Yeah. All right, can you see that?
Yes.
All right, I'd like to acknowledge my co-authors, Nick Peditella, Cora Randall, and Erich Becker, and I'd like to acknowledge NASA for funding this work. Here's an outline. I'll briefly motivate the work by reminding everyone how the vortex acts to couple the Sun-Earth system. This aspect has led me in the last few years to look at the vertical extension of the vortex into the upper mesosphere. Here we compare 14 years, that's 2006 to 2019, winter zonal winds in Whack-A-X Dart at 90 kilometers to zonal winds derived from SABRE geopotential height observations. The time period focused during the year is January and February in the Arctic winter when SABRE is looking toward the Northern Hemisphere. It's well known that Whack-A zonal winds at the polar winter mesopause exhibit a strong easterly or westward wind bias. One explanation for this is that the model omits higher order gravity waves and thus the eastward drag caused by these waves. The point to take away from this work is here we show for the first time that the model wind bias, it's not constant in time, but it's highly variable. The time variation in the wind bias is largely driven by non-orographic gravity wave drag and filtering of the gravity waves by the stratospheric polar night jet. And there's improved model fidelity in the polar winter mesosphere, lower thermosphere during stratospheric warmings. That's what we find. So just to motivate the work a little bit, these schematics summarize the processes whereby the polar vortex couples the Sun-Earth system in the polar regions. On the left shows that the solar wind, solar proton events, and high-speed streams continuously bombard Earth's magnetosphere with energetic particles. Magnetic field lines converge at the poles, and particles precipitate and generate nitrogen oxides or NOx in the stratosphere, mesosphere, and thermosphere, depending on the energy of the precipitating particle. Since air descends in the winter polar vortex, this transports the NOx down to the stratosphere, where it can then destroy ozone, shown on the right. Since ozone is a radiatively active gas, changes to ozone impact the temperature in the polar regions. Changing the temperature gradients then affects the background winds, which affect the upward propagation of waves. So the whole system is coupled. Notice the question marks in the upper mesosphere of the schematic that appeared in the last decadal survey. There remain uncertainties regarding both NOx sources and transport processes responsible for observed MLT NOx abundances. And state-of-the-art models continue to underestimate NOx in the stratosphere and mesosphere, so we need to better understand both the sources of NOx and the transport in 3 dimensions. So this motivation has led me in the last few years to explore the vertical extension of the polar vortex up to mesopause altitudes. This JGR paper in 2019 showed that the vortex in the specified dynamics version of Whack-A is well reproduced up to about 75 kilometers. That's in the bottom row there, but at 90 kilometers in the top row, there are large differences. So here we've got polar maps in the southern hemisphere winter, June, July, August, mean geopotential height in the model on the left and in MLS in the middle, and then the differences are on the right. And at 90 kilometers, the top row, the mean winter geopotential height maps show circumpolar anticyclone in the model, whereas the observations show a strong circumpolar cyclone. At this altitude, the zonal winds at high latitudes are easterly in the model, as indicated by the dotted lines in Whack-A, and they're westerly in the observations, so the solid lines. These results at 90 kilometers are consistent with the known easterly wind bias in the polar winter upper mesosphere of Whack-A that has been reported by numerous studies for over a decade. Most recently, Neil Hindley and co-authors compare Whack-A winds to meteor radar-derived zonal winds near South Georgia Island in the southern hemisphere. They say, and I quote, "This easterly wind bias is well known and may be considered as one of the most significant biases in numerical simulations of the MLT with important impacts for MLT chemistry. There's a growing body of literature that suggests that this reversal of the modeled zonal winds could be due to an incomplete representation of drag due to gravity waves, in particular secondary gravity waves." So it's not surprising that this easterly bias is also present in the DART version of WACM with data assimilation. Here we show monthly mean polar maps of the zonal wind at 90 kilometers. WACM is on the left, SABRE-derived zonal winds in the middle, and the differences on the right. Monthly means for January 2006 are given on the top when the model is in reasonable agreement with the observations. But then in February, just a month later, on the bottom, there are strong circumpolar easterlies in the model that are not observed. So the data assimilation that acts to constrain the model does not overcome the effects of the gravity wave parameterization. If you look at the daily evolution of geopotential height at 3 altitude levels, going from the bottom to the top in the lower, middle, and upper mesosphere, with WACM on the left and SABRE on the right, during January and February of 2006, when SABRE is looking toward the Northern Hemisphere, there's good agreement between the model and observed geopotential height at 50 kilometers and 70 kilometers all the time. But at 90, the two disagree after the January sudden stratospheric warming. And I'll play this again. You see both the model and the observations at 90 kilometers initially show a low pressure center migrating around the hemisphere, but in the model, this low turns into a high that is not borne out in the observations. So during this 2-month period, meteorological conditions in the stratosphere were such that the vortex was disturbed in January 2006 by a major stratworm, but in February was characterized by an undisturbed polar vortex. This is an altitude time plot of planetary wave amplitude at 60 north, and it shows planetary waves in the stratosphere and mesosphere were large in January, followed by stronger planetary waves in February. It's when planetary waves are large and conditions are disturbed that the model and SABRE geopotential height maps near 90 kilometers agreed. So with that background, here I show 14 years of WACM-X DART and SABRE daily average zonal mean, zonal winds at 90 kilometers for all January and February days in which SABRE looked toward the Northern Hemisphere. WACM is the black contour, SABRE's in green, averaged over a broad latitude range polar to 40 north. The WACM and SABRE zonal winds are uncorrelated at this altitude, as indicated by both the correlation coefficient and the anomaly correlation coefficient. Major stratospheric warming days are in red, minor stratospheric warming days are in yellow, and the black line is often in the negative, while the green line largely remains in the positive, reflects the easterly model bias. Looking at the time variation in model wind, it's clear that during strat warms, there's better agreement with the observations. So here's the time series of the model measurement differences. So just the model minus the observations at 90 kilometers. You can see that the easterly wind bias, it's not constant in time, but it's highly variable. And variability in the differences is largely driven by variability in the model winds, since the observed winds remain weak westerly most of the time. And again, this shows that the model's in better agreement with the observations during strat warmings, as in the differences are closer to zero. If you superimpose the planetary wave amplitude in the mesosphere, here the blue line, it's highly correlated with the model measurement differences. In the model, there are westward winds when planetary waves are small. There tend to be eastward winds when planetary waves are large. This isn't surprising, it's just, I don't think anybody's shown the time variation before. Shown here is a scatter plot between the model measurement differences at 90 kilometers along the x-axis and the planetary wave amplitudes in the mesosphere along the y-axis. You can see that model easterly wind bias, that the points are clustered over here on the left side, tends to get smaller as in the points move towards zero as planetary waves grow. This relationship is especially clear during stratospheric warmings, where the correlation increases from 0.5 up to almost 0.9. It's no surprise what's going on. The reason behind the planetary wave wind difference relationship is in the gravity waves. Here we've got altitude time sections of Wacom zonal mean zonal winds and the color contours, and gravity wave drag in the black and red contours, standing for either westward or eastward drag due to orographic waves on the top, waves emanating from frontal systems in the middle, and convective sources on the bottom. And the x-axis is January, February 2006 again, and the y-axis ranges from the surface to 150 kilometers. And gravity wave drag due to frontal sources is an order of magnitude larger than orographic. The contours here are every 20 meters per second per day versus every 2 meters per second per day. So if you focus on the middle panel, you'll see that the gravity wave drag in the MLT is opposite the sign of the stratospheric zonal wind. To summarize, when the stratospheric zonal wind is eastward, strong westward drag atop the polar night jet reverses the jet toward the west. And since there's no higher order gravity waves to offset this effect, you get the wind bias. But when the stratospheric zonal wind is reduced or reversed during stratospheric warmings, this results in eastward gravity wave drag in the MLT, these red contours, and winds that are in closer agreement with the observations. And this behavior occurs during all stratospheric warmings. Again, it's not surprising. This is all probably really of course we knew that, but I hadn't seen it. It was just zonal means of the wind bias. So I'm now looking at strat warming time periods and exploring the vortex during those times when the wind differences are minimized. So to summarize, there's the well-known easterly wind bias in the polar winter upper mesosphere of the model, and many high-top whole atmosphere models, likely due to the emission of higher order gravity waves. And Nick is going to investigate this by running the model at higher spatial resolution to see if the bias is reduced. Here we show that the bias, it does not persist just equally in time across the board. It fluctuates wildly and is smallest when the winter stratosphere is disturbed. And the mechanism is that reduction or reversal of the stratospheric polar night jet allows primary non-orographic gravity waves to propagate into the MLT and drive the flow eastward. And since the jet speed is reduced when planetary waves are large, planetary waves, their amplitude may be a useful proxy for model fidelity in the polar winter MLT. Thank you.
Thank you, Lynn. Are there any questions?
Can I ask you a quick question, Lynn? This is Valerie.
Yes.
Do you remember what's the maximum horizontal wave speed in this runs? Or maybe Nick remember for non-orographic gravity waves, non-stationary gravity waves. It's 65 or?
We did not change anything, so it should just be
change.
the standard setting.
Standard setting, okay. Thank you.
And just a quick comment, if there are no other questions. Hanli has run the free running version at higher resolution and does see it tends to address this bias. And I think he will present more of that tomorrow. So if there are no other questions, Valerie, do you want to go ahead and share your screen?
Thank you, Nick. Can you see it?
Yes, it looks great.
Okay, thank you, Nick. So today I would like to speak about Goddard-Eoff observing system meteorology that we use in the whole atmosphere model since 2012, especially for whole atmosphere model extending in the thermosphere. And I would like to review the recent fascinating results, what we got in vacuum, SD Vacuum X and whole atmosphere of an ANCAR and whole atmosphere model of NOAA's CU Cyrus driven also GEOS meteorology. And this runs was made at the moderate resolution 2 degrees, and now it's time to move to a high resolution meteorology and high resolution version of whole atmosphere model. And I would like to touch several challenges, issues, what we will encounter when we try to do high resolution runs with high resolution meteorology of GEOS. So briefly, the GEOS analysis performed in the Goddard Space Flight Center by Global Modeling and Data Simulation Office is used so-called grid point statistical interpolation algorithm of operational numerical weather prediction system of NOAA and GMAO. And the product is from the surface to roughly 1 Pascal or 80 kilometers. And GMAO provides instantaneous and time average product. It's currently we have three streams of GEOS product which we use. This is modern era retrospective reanalysis for research and application version 2, described by Ron Gilara in his review paper in 2017. Model data's and data simulation aspects is done in MOLET 2015, and Lawrence Tucker's it's 2018. So it's product represented by 3-hourly fields stored on roughly half-degree let long. And it's based on the 2016 version of GEOS 12 with 3D VAR system, which is run from 1990 to the present. So in our whole atmosphere nudging specified dynamics, specified meteorology studies, we use usually instantaneous fields, especially for upper atmosphere application, because we need to reproduce basically instantaneous forcing of tides in the stratosphere and the low atmosphere. So we're going to use instantaneous only fields in our application. Also, GEOS 5 so-called forward processing system, it's basically oriented on near real-time application and operational weather forecasting system. It has also 3-hourly archives with double increased resolution of quarter degree, and who interested can look at this link, HTTPS, which is described in detail the specific of this system. So the whole atmosphere model extended in the atmosphere, which is I will be talking, it's CESM finite volume vacuum X, described by Han Lee and also presented by Nick recently. And also whole atmosphere model of NOAA, this is global spectral model, dynamical core, which is presented by Tim Fuller in 2020. And I also made several presentations about VAM driven by GEOS meteorology. I would like to basically to highlight what VAM since July 2021 is operational model of Space Weather Prediction Center. And before talking about results, I just would like to highlight how GMAO produce with assimilated products. So basically, we have so-called incremental analysis update algorithm, which is applied in both in data simulation and the so-called replay studies, which is basically solicited to produce GEOS GCM application for stratospheric chemistry transport. So here we have the two system is driven by so-called analysis tendency, which is computed for analysis time at 0 UT as difference between the analysis performed during 6-hour collected observation and difference between the forecast. And dividing by 6 hours with this data simulation window, the system turning back on 3 hours and produce so-called analysis tendency corrector step. This corrector step is needed basically to get the balance assimilated fields, which is we use in our specified dynamics, specified meteorology studies. If we use just only raw analysis, so we have some shock and jumps, and this unbalanced system can create additional difficulties in the process of performing specified dynamics, specified meteorology studies. One thing that I would like to highlight on this slide, so we use the GMAO use constant time-invariant analysis tendency forcing in the corrector step. If you're familiar with vacuum SD vacuum, specified dynamics vacuum nudging algorithm, so you probably know that we use so-called relaxation timescale 50 hours, relaxing at every model time step to the analysis interpolated in time. So in specified dynamics, we use time variable adjustment forcing. You can call also analysis tendency forcing. This is linear interpolated in time. For VacuumX, for instance, this is time relaxation 50 hours, and for time step is 30 seconds. Roughly, we're blending model state XM and analysis state XA with weighting like just 0.70%. This nudging is good to reproduce again chemistry transport studies because we quite accurately follow zonal mean flows, planetary waves. But when we go to divergent mode, like gravity waves and tides, so we have internal subdiagonal variability. So for instance, for semidiagonal tide, we have only 4 points for given day to describe a semidiagonal oscillation. This is basically below 45 kilometers where we have ozone tidal forcing. And if we use linear interpolation, sometimes we can degrade tidal performance by whole atmosphere model itself, like free running model. So I just would like to show what fascinating results we got during last 10 years during stratospheric warming events using vacuum SD runs. This is basically strat warming events influence of total electron content. And you can see that after warming, stratospheric warming events, we have global increase of semidiagonal tidal energy, which is shown on the left top plane. This is anomaly of global energy of 12-hour modes. And you can see after 5-6 days in the MLT region, in the ionosphere, you can see basically significant application of semidiagonal tide, which gives different diurnal cycle, which is with semidiagonal tide prevails our diurnal, it produces different total electron content variability. This was nicely produced vacuum SD, and agree with GNS tech observation. This is the next plot where you can see variation of GNS tech along 75-degree west longitudes as a function of latitudes in universal time. So the basic idea of the anomalous behavior of tech, it's prevalence of semidiagonal time driven by specified dynamics of geos can produce the right diurnal variation of tech after the warming events. And this is the second highlight what I would like to make. This is tidal QBO in the diurnal tide at 95 kilometers. Here you can see the amplitudes of temperature and meridional winds on the temperature top and meridional winds on the bottom. And you can see VacuumX results in red and timed cyber DW1 amplitude estimates performed by Dave Fortland in blue. And you can see basically that with specified dynamics, produce very nice results and much amplitudes of diurnal tide at 95 kilometers at equator and 21 degrees south. So another thing what's also related with stratospheric warming, what we found, it's amplification after onset of stratospheric warming, quasi-2D wave amplitudes around equator. And we like it that we have Indonesian Kata-Taban collection for several years of meteor radar. And we can do sample Vacuum-X GEOS-5 results along this location. And you can see without even a simulation of any data above 45 kilometers during 2009, 2010, and 2012 warming events, we nicely reproduce the morphology of quasi-2D wave, which can match the radar measurements. In 2013 warming events, we don't have this generation of regular 2D wave oscillation after the warming. And this is still a big question why we don't have. Probably it's somehow related with higher solar activity and geomagnetic activity during warming period in 2015. In whole atmosphere model, we use the similar techniques and data to perform nudging for several years, perform specified meteorology runs for different years. But in this whole atmosphere model, we try to replicate the so-called incremental analysis updates, just using only constant time-independent forcing between analysis. And having this 4-year runs in VAM, we can reproduce nicely the cubio in the diurnal tide in 95 kilometers. Here you can see VAM specified dynamics run for meridional winds amplitudes and temperature amplitudes on the right, comparing to tidy timed observation collected also from the same periods. And you can see during the westerly phase of QBO, you can significant 2 times amplification of amplitude of winds and temperature. Also, you can see basically longitudinal variability of diurnal tide amplitudes in both data and model maps at 95 kilometers, match themselves quite well. And to continue about this longitudinal variability, even probably 6 years ago, we remember that from the NIC paper 2014, we have a lot of differences between whole atmosphere simulation, especially in terms of evaluation amplitudes. Now, when we do appropriate nudging and specified meteorology test, ingestion of GEOS meteorology, so we have more or less comparable distribution, especially diurnal amplitudes of temperature in winds between Vacuum-X GEOS and VAM GEOS-5, and the color bar on the same, and you can see this is 4-peak structure around the equator in temperature amplitude, which is quite well agree with cyber temperature amplitudes at 95 kilometers. If we continue to look and compare 2 whole atmosphere simulation with GEOS, so and look at the zonal mean distribution, in particular Vacuum-X 2009 and VAM 2009. So you can see basically that the zonal mean winds, I pick up the slice around 45 south, above say 60 kilometers, start deviate significantly. And Jocelyn mentioned that we know that Vacuum-X has this reversal bias in polar region and also in mid latitudes. And looks to me that it's, of course, relevant to the non-stationary gravity waves. And our tune-up of non-stationary gravity wave VAM basically produce probably more reasonable behavior of MLT winds, which is comparable with Europe climatology, which is on the lower right panel. So we also look at the different representation of the zonal mean wind fields and tidal amplitudes on vacuum X, SD vacuum X 2 degree versus 1 degree. And this is based on the Geomagnetic runs, which is provided us, and we make a quick look. And what major decision conclusion is that 2 degree simulation of MLT usually have a bit colder summer polar mesopause here comparing to 1 degree. And also systematically we can see enhancement of tidal amplitudes at 1 degree resolution comparing to 2 degree resolution. And this was moderate simulation of specified dynamics, specified meteorology. What will be next for forthcoming years and upcoming configurations of GEOS? And we would expect in 2022, 2025, which will lead us to transition to so-called MERA 3, which is probably will be started in around 2025. First, we will having the new GEOS atmospheric GCM with finite volume dynamical core on the cube sphere, reviewed by Bill Putman 2021 on a June meeting. This is 180 layers with enhanced vertical resolution in the cuboid domain, also enhanced resolution in horizontal between 3 to 12 kilometers, and of course upgrades of gravity, model physics, including convection and gravity waves. And we would expect also new couplet data simulation system based on the Joint Center for Satellite Data Simulation Initiative JEDI with 4D INVAR algorithm, which is a replacement of grid points statistical interpolation. But between 2022 and 2025, GMAO is planning to run so-called GEOS reanalysis for 21st century. This will be still 72 levels model, but at the enhanced resolution, 2 times horizontal resolution, roughly 1/4 degree or 25 kilometers, with latest hybrid 4D INVAR data analysis system and using NASA's EOS and POST-EOS data. What kind of benefits we would expect from this new system, especially GEOSR 21C next 3 years? So we would expect to get hourly archive for better representation of tidal forcing below the stratopause. We hope to resolve gravity wave spectra in this high resolution run. We also will get consistent aspect ratio between vertical and horizontal resolution. And finally, we would expect rapid data ingestion. To highlight some problem about mesoscale gravity wave dynamics and gravity waves in the analysis, I plot on this slide the global kinetic energy spectra evaluated from different analysis system, GEOS 5FP and MERA 2 at 2 altitudes 30 and 65 kilometers, and 3 model, whole atmosphere model, VAM-T62, VAM-256, and Vacuum X. Vacuum X and VAM-T62 correspond roughly 2 degree resolution, and VAM-254, it's 50 kilometer resolution, which looks like MERA. So you can see basically that MERA 2 and GEOS F5FP, driven by different models and different data simulation system, have different behavior of kinetic energy spectra and mesoscale. So we do expect that GEOS 5 forward processing, which is used in operation, can be much better in representation of gravity wave dynamics. And I need to mention that both NASA and NOAA moving to the non-hydrostatic finite volume dynamical core on the cube sphere. And free running model has excellent capability to perform the mesoscale dynamics, which is you can see on the right. This is FFGFS free running model at different resolution, 12.5, 25, and 100 kilometers. And you can see how with different configuration can reproduce above wave number 40, roughly 4,000 kilometers wavelengths, minus 5/3 kinetic energy spectra. But having this high resolution data simulation product, we need to properly to ingest this information in our models to keep the gravity waves in the business if we start to resolve gravity waves. The current feature of the Meteorology analysis, for instance, due to half-degree resolution and higher horizontal correlation length with spread information from the data points to the adjacent model grids, with this correlation length more than 1,500 kilometers, produce smoothing of the mesoscale features. That's why probably MERA2 cannot reproduce minus 5/3 tails in the mesoscale subbranch. And what we will see basically that the modern dynamical cores can reproduce a lot of gravity wave structures. So this is from my paper 2021, where we do diagnostics of FFGFS 12-kilometer resolutions, and this is absolute momentum fluxes of gravity waves at January and August, January top, August below. And if we compare with Hurdle's estimates of absolute momentum fluxes at 10 hectopascal height, so you can see that basically model can resolve a lot of gravity wave hotspot activities. And so it's better to think about how we can preserve with gravity wave activities during the specified dynamics, specified meteorology runs. And so I was basically pleased to—
Valery?
Yes, I
You're a
will
bit
finish.
over time, so if you could wrap up soon.
Yes,
please.
I will. Thank you, Nick. So this is basically the last highlight slides, which is I would like to put with us highlights from the Eric Becker paper 2021, where he basically ran his higher altitude gravity wave resolving mechanistic circulation model. And he demonstrated that to preserve gravity wave signature in the specified meteorology, specified dynamics run, we need probably to perform so-called spectral nudging, which has different relaxation rates for different spectral modes. And you can see below how different they are. So basically the idea is to nudge only resolve scales, which is quite nicely reproduced by GEOS 5 analysis, and left behind nudging with scales which cannot be properly reproduced. And how he validates with this IRIS data of temperature perturbation, with this MERA2, and with this his spectral nudging of his model by MERA2. So, and concluding my conclusion, the current forthcoming use of GEOS meteorology and whole mesosphere models at the enhanced resolution will require optimal archiving, 1 hour condense of GEOS products, and resolution-aware formulation of specified meteorology schemes to realistically represent the diurnal cycles and mesoscale dynamics in the nudge domain. So we probably need more validation of this specified dynamics, specified meteorology runs at high resolution. And luckily we have new data in the thermosphere which can be used for evaluation with fascinating model runs. Thank you.
All right, thanks, Valery. In the interest of time, I think we should move to Dan's presentation. But Julio does have a comment in the chat that maybe you could address, or we
Thank
can
you.
discuss in the discussion time period. So Dan, do you want to go ahead and share your screen?
Yeah, can you see that okay? Does that work?
Yes, it's not in the full screen, but it seems large enough.
Okay. Yeah, I'll just stick with that just in case.
Yeah, it's fine. I mean,
Okay. So I'm going to talk today about new methods for specifying solar and geomagnetic forcing in CSM. This is work that I've been doing with Francis Vitt and Max Grover. And to motivate why we want to do this. So we know that for the upper atmosphere, we're interested in solar spectral irradiance variability and UV variability for a number of reasons, but primarily it's because it drives heating and chemistry and photolysis in the stratosphere and mesosphere, and so that has potential implications on dynamics and the way in which the regions of the atmosphere couple. So this is just a schematic from a review paper by Annika Seppala. That's the solar part, but there's also the geomagnetic forcing, and the way that we do that, there are a number of ways that we do that, but one of them is through the specification of energetic particle precipitation in the model. So this would be things like what's going on in the auroral regions, solar proton events, and electron precipitation that can make it all the way down into the lower mesosphere. And the primary effect of that is to create Hawks and Knocks, which will then participate in catalytic cycles. It can also destroy ozone and similarly affect the radiative balance in the atmosphere, and so similarly affect dynamics and the way that and this is also another way in which perhaps layers can couple. Okay, so that's motivation. How do we do it? Well, in WACM, for the previous CMEP cycle, we used the recommendations of these drivers from the Solaris HEPA community, and the specification of that is described in this paper in GMD, Solar Forcing for CMEP, led by Katja Mathis. And what is included in that is that there's a solar irradiance, or spectral irradiance, and TSI for the pre-industrial control, the historical period from 1850 to 2014, and then a single scenario going forward for the solar variability from 2015 to 2300. Also included in that file is the F107 index, the geomagnetic indices, AP and KP, and then these ion pair production rates from protons, electrons, and galactic cosmic rays. So how does it go about specifying a future scenario for the solar variability? Well, what it does is beginning in January 1, 2015, it starts to pick out selected prior or historical cycles and repeat them. So if you're running WACM after 2015 and you're just picking up one of the SSP scenarios, you're actually running solar variability from 1883 to 1890. So that's something that perhaps people aren't always aware of. And what motivated this particular work was that we needed a way to update those forcing files. So they have the Solaris HEPA community has issued an update to that forcing, which covers through 2019. And I think, probably every 5 years or so that we'll expect to see a new reference solar spectrum, so up to relatively present, say within a year. But really what we need is tools that can create forcing data sets in almost near real time, for the recent past, and even those to go into things like space weather forecast models or S2S predictions. And I think that even persistence is likely better than using fluxes from 1891. I think you might agree with me on that. Okay, so how do we go about creating those data sets? Well, we've created some new tools that you can download. They're in a public repository on GitHub. So it's under github.com NCAR Solar Forcing. And you can simply clone this repo and download the tools necessary to create your own forcing data sets. So this is a relatively new project. It's been put on a public repository because I'm hoping that people will help maintain, expand, and work on documenting these with me in terms of generating a tool for the community. So this is relatively new, and but I was excited to share this with you at this working group meeting. So there is some documentation we started, generated from Jupyter Books, talking about taking some of the notebooks that are in this repo and describing them a little bit in detail about what parts do in terms of this API to create new forcing data sets. So that's the URL. So I guess if you're on YouTube or what you say, you can pause and copy that. All right, so the first task to do is to update the solar spectral irradiance data file. So once you've downloaded and installed this package, this repository, you should be able to open up a notebook. And within here, I've essentially created a ozone data set and made a few plots in a matter of about 6 lines here. I mean, if I didn't do the plotting, it would be maybe 3 lines. What I've done is I've pulled, so you start out with saying importing solar radiance from the solar forcing repository. And then you can extract from the web solar irradiance, and in this situation I pulled from the LASP lizard NRL2 or NRL SSI2 preliminary data. So this is one that goes at least up to the middle of June last year, and so that's this line here is how you can extract that data set. And then this next line just shows you what I extracted here. So if I look at that line and say what actually have I downloaded, I've downloaded 91 days of preliminary data in 3,785 spectral bands, and it gives you the dates that the file goes from. So it starts in the 4th month, beginning of the 4th month here in 21st. And so it gives you some data. But this is not exactly in the format that we need for importing into Wacom. So we then call this method called generate dataset, which recasts it into things that Wacom expects. So for instance, here now it's called TSI, and it puts on a date variables that Wacom is used to seeing. And you can see here that there is TSI and SSI. So here I've just simply said irradiance ds tsi.plot. So I'm just plotting out the TSI out of this particular data set, and we can see that over these few months it went from, it increased, the radiance TSI increased from about 0.3 watts per meter squared. Or I could simply say give me the last entry in the file, time equals 90 here, and just plot the full spectrum on a log plot. And then if I want to create a file for the forcing Wacom, I just say to netcdf and give it a file name. So that was, then you can put that into your name list, and you, if it covers the right time period for your simulation, you'll be able to run with the observed latest solar variability. Okay, so what about medium energy electrons? This is another aspect that often needs updating if you're interested in looking at stratospheric ozone or mesospheric ozone, and you want to get the right variability due to electrons coming from the Van Allen belts. And so the way that that was done in CMIP, and the way that we're following it here, is that there was Van de Kamp parameterization. It's in this reference here. fit the AP index, AP index, takes the AP index and fits or returns a energy spectra on geomagnetic L shell. And that's essentially zonally symmetric in magnetic latitude. And from that, we then call the Fagnetal monoenergetic energy deposition code, which over the bands that we've created here. And so they're flexible in the code, how many bands you want to choose, and performs a vertical calculation of how that energy in each band is deposited in the atmosphere. And then from that, with that energy deposition rate, you can directly calculate an ion pair projection rate. So in order to do that, you need the AP. And so we can now have a way of grabbing that data from the GFZ Potsdam database. There's an ASCII table here that's available via anonymous FTP. So, and this is essentially nowcast. So, and going back for decades. So, if you wanted to do a storm even from yesterday, you could actually do it. So from that, we're pulling down an AP, just an example of an AP value here of 54 on an L shell of 5. And then this is what would be the energy spectrum returned from the Van de Kamp parameterization. These are just a few slices of different energy bands of the energy deposition rate from the Fagnetal, and you sum all this up and you get a total energy deposition rate. So this is done at each L shell on each day that you give it an AP. So how does that work in practice? If you were to download this repo, well, you say, I want to perform a flux calculation between a start date. So here I'm doing 2022 to yesterday. I go and grab the data from the repository. I calculate those fluxes, and it returns here a ion pair production rate, and also just the AP values that happen to be going into that file. And then I can again save those out into a netcdf file. Okay, so those are the two tools that operate in a sort of Python universe. Francis took my Python code that sort of created these and turned it into Fortran, and now we've been able to inline it into the code. So it does add a little bit of overhead, but we already have the AP index in the Solar Parms data file. And so that these two components now have been turned into Fortran. And so that we can now have, as long as this file is updated, we can actually have the medium energy electrons calculated as the model runs. So that's, I'd say, coming soon. I think Francis has put this into the development trunk already of CAM, and so in the next release this will be available. So the previous methodology works if you want to run something right now. And this should be available very soon. But it opens up a new possibility. So this was if I said do, in the nameless option, medium energy electron ion inline equals true. Another option is to say, actually, I want to specify the fluxes at the top of the atmosphere for medium energy electrons. So in this case, you would give it a file. This is a file consistent with files that would be generated from the Python. So in this situation, you could actually take the same Van de Kamp parameterization and generate a netcdf file of the energy spectra as a function of L shell and time. And then that is read in, and the inline deposition is calculated in the code. And so this opens up new possibilities. So for instance, if you don't want to use what we would call the APEEP or APEEP parameterization of Van de Kamp, we could be taking something from AMI, as long as it comes in on a format which is L shell, then an energy spectrum. So this doesn't necessarily have to be this power law distribution. It could be something else. It can then be fed directly into Wacom inline deposition code. In the future, I'm hoping we're going to be able to get some of these fluxes from magnetospheric models such as Gamera, or if there are other observational data sets that are available that could generate these energy spectra on L shell that also could be used to drive the inline code. So that's some new features that we put in. I'd like to acknowledge that this was supported in part from a CETA grant on quantifying the impact of radiation belt electron precipitation on atmospheric and reactive nitrogen oxide and ozone. So with that, I'll take any questions.
Thanks, Dan. Lynn did have a question that she typed in the chat. I don't know, Lynn, do you want to just ask Dan?
Yeah, Dan, you're probably familiar with Josh Pettit's MEE data set. I was just wondering if there are any plans to include other MEE data sets in addition to what you have plugged in here.
That I think was part of the motivation of splitting up these steps so that you know, you can bring your own your top of the atmosphere fluxes. So we may be expanding in the future where it's not simply just on L shell, but maybe would be L shell and magnetic local time or something like that. But that was the idea that of sort of splitting these various processes, that it would open up the potential to drive it with other data sets.
Thanks.
And Dan, I actually have a question as well.
Yeah.
With the Python code, is there a plan to, maybe it's already included, or I'm not sure, also have, you know, updates for F107 and KP, AP files for, you know, the solar palms file?
Yeah, I don't see why not. We should be able to expand this tool to make that. That one was a really simple file to make. It's a very simple netcdf file that just has time history of F107 and AP. I have some IDL code that was used, and I think it's been updated. But it would be nice to incorporate that into this package as well. We already know that we can pull the AP from the Potsdam data set. So that's in the file, in that MEE file already. I don't see why not. Like I said, this is a GitHub repo that is out there now. I'm hoping people will say, okay, great, I'm going to build on this and push back additional tools to the community, as opposed to us leading it. I'd be very happy if the community participated in this. And of course, this is a tool that could be used for, other models. We're just essentially giving the tools that were used for CMIP out to the community. I did validate this against what was downloaded from CMIP, and it was pretty close. Certainly within the uncertainties. There are some very minor differences depending on how you select an atmosphere or the size of the bounce loss cone that you use. This is the main reason to do this, honestly, was I'm hoping this finally gets dug to ditch IDL.
Good luck with that.
All right. I think we have about a minute and a half or so for discussion before we have a short break. Is there anyone have question or comment on any of the presentations or anything else? If not, why don't we conclude this session here? And I think we will take a short break and reconvene at 1:30 Mountain Time.
Thanks, Nick.
everyone. Welcome to this afternoon's session on CSM and CAM physics and sensitivities. My name is Nick Davis. I'm one of the co-chairs of the whole atmosphere working group. Just a reminder to our speakers today, as before, you have 15 minutes, but it would be good to leave a minute or two for questions and discussion afterward. So when you're talking, when you have a minute left, I might hop in and say 1 minute left to go. And then if you can wrap up and we can take any questions. And we also have a discussion period scheduled at the end for 2:45 Mountain Time. And then we'll adjourn at 3. So our first speaker today is, Our first speaker today is David Mitchell, who's going to talk about Calypso cirrus cloud retrievals and comparisons with WACM.
Good afternoon, everyone. This is improvement on a remote sensing, cirrus cloud remote sensing method that we developed several years ago with the hope or intention to improve climate models. So this is a collaborative effort, of course, with Anne Garnier that helps that I'm a collaborator with on the remote sensing, John Mejia for the modeling, and Sarah Woods for the microphysics field data. And this technique is draws heavily upon field data, field campaigns. The previous method used the ice water content to get the number concentration. And we wanted to avoid that because it's hard to know exactly what the ice water content is. So we replaced it with the area, projected area of the size distribution of ice particles. And so this is the formula for the number concentration. So we go out with, in a field campaign, measure the ice number concentration and all these things. We measure that projected area, and we retrieve the optical thickness at 12 microns. And we can also, from the size distribution, calculate the absorption efficiency, and the satellite measures the thickness of the cloud, delta Z. And some of these quantities are formulated in terms of the effective beta, and beta is the ratio of the absorption optical depth at 12 versus 10.6 microns. And the key here, or the game we're playing, is to relate microphysical quantities to this beta. So the estimation of the ice water content has been improved here, and it's based on better estimates by this recent paper, Rafani and Mitchell, better agreement between the predicted values of ice water content versus those retrieved, and a recent laboratory study of ice particle masses by Wetzel et al. So number 3 here is the equation we're using to get the effective diameter. It's based on theory. This is a fairly well-known equation on the left side, and that's expanded to express it in terms of retrievable terms on the right side. So N over A and ice water content over N, the number concentration. So to go a little deeper on what I just mentioned, there was a study by Wetzel et al. In 2020. In a laboratory study, they measured the masses of ice crystals, and they focused on the really small crystals, less than 100 microns, and that's shown by this dotted curve or line here. The slope isn't probably correct, but it's in the right ballpark. The magnitude of the measurements are definitely in the right ballpark, and they agree with the Rafani-Mitchell mass measurements and also those from Lawson in 2029 at small sizes. And so that was encouraging. We also compared this parameter beta that's retrieved by satellite, shown by the color. Cool. Anyway, We also measure beta by the size distributions that are measured in the field campaign, and those are shown by the red triangles. So when we use the Irfani-Mitchell mass treatment, we get pretty good agreement between the aircraft observations that will we predict the beta value from the aircraft measurements, and then we retrieve this black curve is the retrieval median value, and they agree pretty well. But when we use a different mass relationship, you can see that the agreement on the right side here, the agreement's not as good. So the bottom line is that it's important to estimate the mass of the ice crystals as good as you can, or your retrieval is likely to be a little off. So this is for the Atrex campaign on the top and the Poseidon campaign on the bottom. Some of the relationships, these are the relationships that we use in the retrieval. And ice water, N over ice water content is pretty universal for all the field campaigns we looked at. Atrex and Poseidon, Spartacus in the mid-latitudes in the US, TC4 off the coast of Costa Rica, and N over the area is the new relationship that we're using here. And it's fairly robust, but it depends a little bit on the field campaign that you're looking at. And then even more so with the effective diameter, it depends more on the field campaign. You get a decent relationship, a fairly tight one in the case of the tropics, the Atrex Poseidon off of Guam. But they are different. So that posed a little bit of a problem in that we're getting two retrievals depending on the region of the planet you're looking at, the tropics versus the mid-latitudes in this case. And that had something to do with size distribution shape that changes between the tropics and mid-latitudes. That was sort of a surprise. And then this other quantity, it also depends on the location or the region. So when we look at we're testing the retrieval here. We test it for Atrex and Poseidon field campaigns. And the temperature is always less than 235 Kelvin, in other words, minus 38 Celsius, the cirrus regime. And the optical depth lies between 0.3 and 3.0. And the black curves give the median retrieve values, and we've got the 25 and 75% quartiles as the vertical bars here. And we, in the Atrex campaign, the effective diameter that's retrieved, the black curve, agrees pretty well with the measurements from the aircraft, and same with the ice water content and the number concentration. With the Poseidon field campaign, it was similar, but we do get higher ice water contents and effective diameter at the at the warmer temperatures. And that might have to do with the aircraft sampling in the lower cloud that the satellite cannot see in really deep cirrus clouds. So this is an example of what we came up with. And we came up with two retrievals, one for outside the tropics and one for the tropics. And we're calling the tropics plus or minus 30 degrees latitude here. So that's what you see on the right side for effective diameter. There's a big discontinuity between the two retrieval schemes. And that's artificial, of course. So we have to use something else to integrate these two retrieval schemes so that they're continuous. And we use temperature to do that. But overall, in the tropics, the concentrations are pretty much in agreement with what the aircraft measurements show. And what we see for number concentration, it's an indication of homogeneous ice nucleation when the concentrations are relatively high. This is for December, January, February. And you can see it's relatively high, especially in the Arctic or the high latitudes. It shows a lot of homogeneous ice nucleation is occurring at high latitudes. And this is seasonally dependent, so you get it in the mid-latitudes during winter for the northern and southern hemispheres. And the ice water content is shown here. And you can see on the right side, this is the average sampling temperature for the cirrus. And you can see that the temperature varies across the tropics. And on the far right is associated with the Atrex Poseidon experiments off of Guam. So the temperatures were relatively cool during those field campaigns. And we can, the Spartacus campaign was in the central US. So you can see that the ice water content and the temperature on the right are tracking. They are very strongly correlated. And the same was true for effective diameter. So because of that correlation, we can use this formula to integrate these two retrieval algorithms or formulations. And X is the retrieved cloud property, and X tropical is what we get with a tropical retrieval based on Atrex Poseidon, and XML is for Spartacus. That's what we retrieve with that formulation, and the temperatures correspond to Spartacus and Atrex Poseidon and the actual temperature that you're sampling at. So this is our preliminary approach. We haven't done this yet, but this is what we're going to do soon. And that should integrate the two methods. So then we did a Wacom 6 experiment where we just ran Wacom 6 for 4 years and compared our results with those published in Gettleman et al. And these are different radiative quantities from Wacom, like long wave cloud radiative effect, short wave cloud radiative effect, and the others are defined up here, net long wave and short wave fluxes for all sky conditions. Anyway, they all agree pretty closely, and the observations are on the right. So we're pretty convinced that we did the simulation correct. And now we can compare the Wacom results with the new retrieval results. Again, you have this artificial discontinuity here, but the overall gist of it is correct. You know, like the average values there are reasonable. So it has the same general character as the Wacom, but the values are much different for the effective diameter. They're lots smaller in the retrieval. For this DJF values, the effective diameter is more than twice as large as the retrieve value and more than around 3 times larger in the mid-latitudes. So in the mid-latitudes in Wacom, it's about 3 times larger than retrieved. Number concentrations are quite different. It's actually kind of the opposite. So in the tropics, you're getting higher number concentrations in Wacom that are, so basically Wacom is missing what we would argue the homogeneous ice nucleation at mid-latitudes and in the Arctic. And so high latitudes are not at all what represented very well in Wacom in terms of ice number concentration. And the reason for this that we think is the reason is the treatment of orographic gravity waves. So here you have the measurements from our retrieval on the left side, and this is a study by Jews et al. On the right side, and this is the updraft velocity that she's got in the upper panel, upper right here, and the lower right panel is the number concentration of ice crystals predicted from homogeneous ice nucleation only. And they match pretty closely the patterns that we're seeing here for boreal winter and boreal summer. Kind of on average, they look very similar. So we think the orographic gravity wave treatment is really important to get the crystal number concentrations and the effective diameters correct. Another study by Barahona et al. In 2017, Nature. Again, we have the updraft standard deviation on the upper left here, and the estimation of homogeneous ice nucleation on the lower left. And they're pretty similar to what the Jews study showed. So you can think of homogeneous frequency as number concentration being high, similar to the Jews study. So overall, this is our summary that the cirrus cloud effective diameter and number concentration predicted by Wacom were quite different from the new retrieval, although there was some similarity in pattern for effective diameter. NI uncertainty is minimized by employing directly measured quantities, like the area of the size distribution and number concentration. The long wave and radar ice cloud radiative properties are sensitive to the shape of the distribution, the size distribution. And it appears that variations in the shape of the size distribution affect these long wave properties and can be roughly accounted for by as a function of the sampling temperature of the retrieval. And then number 4, comparing the retrieve number concentration with other modeling studies strongly suggests that much of the difference between predicted and retrieved values is due to the treatment of the orographic gravity waves. And also ice number concentration, ice nucleating particle concentrations should also be improved upon. They should be a lot lower probably in the high latitudes to get the homogeneous nucleation going there. And finally, a methodology for constraining the CAM using these satellite retrievals is described in this recent paper. And this methodology was used to estimate the radiative contribution of homogeneous ice nucleation relative to heterogeneous ice nucleation. It was discovered that constraints imposed by Wacom 6 were violated in this experiment. And we are seeking anybody out there that would like to collaborate with us who has good CAM debugging skills. So basically we're stuck right now and we could use some help. So if anyone's interested in collaborating, just contact me at that email address. Thank you, that concludes the talk.
Thanks, David. Especially with related to your last point there, this is maybe something we should discuss in the discussion section at the end. Maybe we can talk the broader group about how we can move that project forward. We are at probably a time we should move on to our next speaker. Thank you. If you can stop sharing your screen, and our next speaker is Trude Eidhammer, who's going to talk about perturbed parameter ensembles in CESM.
Okay, let's see. I guess I should put it in slide mode. So this is work in progress, and so you're trying to understand sensitivity of the climate with a perturbed parameter ensemble in the CSM model. I'm going to talk some about this ensemble here. So our motivation is to understand the community Earth system model sensitivity of climate to several different parameters. And also to learn the uncertainties in climate sensitivity. And also we can use this to tune the model too. And the tool we're using is the perturbed parameter ensemble. And also the initial goal of the PPE is to understand the parameters, the sensitivity of the parameters in the mean state climate, and also aerosol forcing and cloud feedbacks. So to create the PPE, we were using the Latin hypercube sampling technique. And just to describe that, so what we can do is that we can do random sampling. But if we do that, so say
Hey,
we
Trude,
have, yes?
Can I interrupt? Are you advancing slides right now? We can't see them.
Yes, I tried to. You can't see them?
We're still in the non-presenter mode.
Okay, let me just use my laptop and this on the screen. Let's see. Can you see it now?
We can't see the presenter. Well, we can see probably your view. We just can't see the full screen mode right now.
Maybe I should just do the slide. Can you see it now?
I can just see the first slide of your presentation. Maybe you want to try to on-share and re-share your screen again. Maybe that might work.
So you cannot see it. You can only see.
I can see your mouse moving on the PowerPoint sort of application.
Okay, let me try again. Okay, what can you see now?
Now we can see your second slide. But yeah,
Okay.
try going to full screen mode now and see maybe.
Yeah, I've had problems with that before.
Okay.
Let me try.
We can see it. That's great.
Okay, but can you see the next one?
Yes.
Yes. Okay. Awesome. Okay. So, so here's some example of sampling. So the first one is random sampling. So you have parameter A and parameter B. But the problem with the random sampling, you can see parameter B has basically the same value for two of the parameters or values. So with Latin hypercube sampling, it makes sure that each parameter has a unique value, so that you are basically allowing for the entire parameter space to be covered. So here's just an example from our results. I'm going to show more later, but this is from shortwave cloud forcing. I just show 3 different parameters. And you can, so the dots here are basically where they are in the parameter space, and the colors are the value of the shortwave radiative forcing. You can see that this sample here basically covered the entire parameter space. So what we did is that we perturbed parameters across most of the cloud physics. So the turbulence, microphysics, deep convection, and aerosol parameters. And we chose 45 parameters. And since we're doing, I mean, with perturb parameters, you can perturb one at a time, but that would require thousands of simulations. But with the Latin hypercube sampling, you can reduce the amount of simulations you need, but still cover the entire parameter space. So we ended up with 250 parameter sets, so basically 250 simulations. And we ran them for 3 years. We tested it for 5 years, but didn't really find much difference. So to reduce the computer time, we are running 3 years. Also, we ran 3 different types of simulations, and this is in order to get the forcing and aerosol forcing. So we ran 250 simulations of present day climate, and then 250 using the same parameter sets. We ran the pre-industrial with aerosols from 1850 concentration. So we can get the aerosol forcing by taking the difference between the present day and the pre-industrial. And also we ran one set with the sea surface temperature increased by 4 degrees Kelvin. And with this one, we can get the cloud feedbacks by taking the difference between the present day and sea surface temperature. So for output, we have mostly mean monthly state, so 181 outputs, but we also have a few daily averages. So, so here's just some initial results, and this one shows the spread across all the different simulations. So the solid, let's see, the dotted line are the control run. So every that is basically the baseline parameters for CAM6, and then the solid line is the mean over all 250 simulations. And also what's showed here is the present day, sea surface temperature, and pre-industrial. And we show the liquid water path, long wave, cloud radiative effect, average cloud top liquid number, and net solar flux at the top of the model. You can see there is a large spread, and you can also see, for example, for liquid water path, the control run is kind of in the tropics here are rather different compared to the mean of the parameters of the PPE ensemble. So here is just an example of the forcing and feedbacks. So we basically take the the present day minus pre-industrial, and the feedback is the sea surface temperature minus the present day. And there is a big spread here you can see between the parameters, all the different parameter ensemble. And this is something that Margaret Duffy is going to work more on. This is, yeah. So we also, what we are doing is that we are taking this into emulators. So we are going to look at different emulators. We have the one developed by collaborators at Columbia University. They have both Gaussian process and neural network. And we also have an emulator developed by a collaborator from University of Leeds, I think, Oxford. And what I'm showing here is I've taken, so I'm creating 5,000 new parameter sets and put it into the neural network emulator. And what to show here is just the long wave cloud radiative forcing outputs as plotted for the different parameters. So this shows the microphysics, variation in microphysics parameter. This shows turbulence, and this shows convection. And the parameters are plotted as they are normalized. Oh, no, they're not normalized, sorry. And what you can see here is that many of these parameters does not really impact the cloud radiative forcing. The one that is just fully color-coded by green and red is, but this parameter here, which turns out to be the ice fall speed, has a large impact on long wave cloud radiative forcing. So this is one parameter we want to hone in on and make sure that we get the best value for that one. And turbulence and convection, it has some parameters too. And I'm going to show you. So what I did as well was taking these same data and finding the slope of the sensitivity. So on the x-axis, that's just all the parameter values normalized, and on the y-axis is the long wave cloud forcing. And also I divided them into different regions, so that because some parameters have more impact in other regions and not in other regions. So so here, next one, I am just showing. So here I'm showing the slope, the value of the slope for different parameters. So so I looked at Southern Ocean, and I looked at the tropics, and looked at shortwave cloud effects, and long wave cloud radiative effects. And these are sorted with the parameter with the highest slope on top. So you can see that there are some parameters that comes in all regions, like this is the fall speed, ice fall speed, which is highly impactful. Another one that is which is highly impacting and also very uncertain is the size of when ice particle turns into snow. And this is something that we've been working on, and actually have implemented the P3 scheme by Hugh Morrison, which removes this this unphysical size limit. So that's something we're going to do and put into PUMAS as well. And you also have like club parameter. This is, I believe, related to buoyancy, and club is also high up there. I mean, there are certain ones that comes again and again in the different regions. So also this is the auto conversion in convection. So by looking at this, you can figure out which parameter maybe to focus on. And this last slide, this is the other emulator from University of Oxford. So that's something we're going to do too, and looking at the different emulators, looking at the difference between them. So here is, again, long-wave cloud radiative forcing. This is the truth from, so it's not observation, but it's what it's trained on. And this is the Gaussian emulator. This is the neural network emulator. And these differences are differences from the truth. There's a scatter plot here. So you can see they all are underestimating the cloud forcing in the tropics here, are doing somewhat, the neural network is doing somewhat better than the Gaussian. But this is still work in progress. So just to summarize, the perturbed parameter ensemble is a good way to probe the sensitivity of CSM physics. So we have 3 sets with 250 ensemble each and 45 or 46 different parameters and over 200 output variables that you can look at. We are working with 2 different emulators to isolate effects of individual parameters and covariance of parameters. And this is a community project. So if anyone are interested in using this data, you can contact me or Andrew. We will happily share it. We also have some script if you are interested in running your own runs. It's simple to just change the name list. You need to have name list parameters for your parameters. And so let us know if you are interested. So that's it.
Does anyone have any questions? We've got plenty of time for questions. You can type them in the chat. Feel free to ask them directly too.
There was a paper by Ben Sanderson some time ago that seemed related to this, and they found that the entrainment coefficient was an important parameter. Did you find anything similar to that? They also found that ball speed was very important, like you were mentioning.
Yeah, I haven't looked specifically at the entrainment, and Andrew, it was one parameter we left out. Was that the entrainment? Do you recall?
No, I'm not recalling. I think it was a convective timescale parameter in the convection.
Okay.
But yeah, the deep convection had 1 or 2 things that were not there. And I think there's something related to entrainment, but I'm not sure.
Yep.
I'll just make the point that DMP-DZ, which is the entrainment rate, is the entrainment rate for the CAPE calculation. It's not the entrainment rate used by the plume ensemble. That is not a name list. It's actually pretty buried deep into the code.
Okay.
All right, everyone. Thanks for your questions. Let's move on to our next talk by Even Selland, talking about the convergence of cloud radiative forcing for microphysical substepping.
Let's see. Do you see the screen now?
Yep. Not full screen yet, just
Okay,
probably.
yeah, I'll put it in presentation mode, that's fine.
Perfect.
So it's a bit of general. So talked about quite a lot yesterday when it comes to this collection of ice number particles. So this is connected to this one, and based on the article from Chu, also going into the substepping. figure on the lower right is the number of partners in the NORSM model. I'm not going into the NORSM models, but for this, presented it several times before, but for this specific, it's mostly, with regard to CAM, is mostly the same, but we have different aerosols, radiation, and a number of energy fluxes and so on are different. So connection between substepping and ice number limiter, impact on cloud microphysics, and then going on to the dependency on cloud forcing for model time stepping. And this is sort of the idea or some discussion with we have Geopotential found this was important for climate sensitivity, in particular for the last glacial maximum, and also that it was found that NRMax had some problems and missing fields, missing numbers included. Two suggest increase the substepping from 1 to 8, and this was decided on ice number concentration. And then just some definition. The first one is two different ways of limiting the cloud ice particles. NRMax is just limiting the part regarding nucleation, and then NICons is limiting the total number of ice number particles, not only this one process. And then there's physics time step, number of microphysics iterations, and then internal iterations of the MG. Simulations is a number set, nominal 2 degree and nominal 1 degree. Quite short simulation, but the results are not sensitive to averaging period. A year basically gives much of the same results that you're going to see here today. The bit of harder part is there's ice nucleation tendency limiter, and the limiter is the two lines that you see. It's and I can't go above the number of pre-existing particles plus the homogeneous and heterogeneous nucleation. And as a limiter, it cannot increase if relative humidity is below, supersaturation is below 5%, or it's warmer than -5. Yeah. And that's what the NIMax. Then the problem was that then was including heterogeneous freezing, that heterogeneous term that was implicit in the old was basically set to 0. Possible solutions: bypass NMX altogether, but limit the total number of ice particles, which is in standard in PUMAS now. And then also tested a less changing version where you just add the tendency to NMX. So still keep the NMX, but then I'm not restraining the other parts of the number. Zonal averages. This is cloud ice normal particles, so 1 or 2 degree, and it's relatively low amount. This is not, the unit is not liter, it's number per gram. So in, for instance, a 200, that would be, guess would be an order of 50 per liter. And the Hofer increased it a little bit, and Chew, which turned off many of the NMX altogether, increased the number by more. One strange thing that I don't really understand is what's going on in Antarctica. It doesn't really matter for the climate results, but it's interesting to see from a microphysics point of view why adding more particles should reduce the number of particles in the end. 2 degree is a very different story. It's the same scale, so that's why so the number of ice particles in 1 degree is order of 10 more than in the 2-degree version. And here we see the limiter kicking in for the Chew, where you get the cirrus, where the outflow from the cirrus makes for a very large number of particles, and it's also happening much higher than in the 2-degree version. Going further down, it's a bit different because actually the NIMAX still actually increases the number towards the North Pole more, and the other way around against the southern hemisphere. So it has some implications, so much in a way the same Andrew, but you can notice that both Chew and Hofer increases the ice water path and reduces the liquid water path, in particular the latter one. And also Chew et al. Increases the long wave cloud forcing by quite a lot. So then, and same with short wave, so the net forcing increases by around 1 watt. No limiter, by the way, is where I just turned off the entire limiter that was also included in Chew. So it's the model runs that way also, but shortwave cloud forcing becomes very large. Then it's look into does these results depend on the physics time steps? And then I ended up with quite a lot of simulations, but they're put together when the results are put together on forcing, total forcing, long wave and short wave cloud forcing, all in the same results. So it's 2-degree where you have Chew or Hofer or standard, and then number of substeps, and then 1-degree where it's also a number of substeps, but also variation on the microphysics and all together physics time step. This is net radiative impedance. So all of them basically start at 1 to 2 watts. The MacMaker is even higher, it's around 5, and then drops down and then continuously go up again as the time step goes down. So it's interesting enough, actually, the last where it decreased the whole model time step to 900 doesn't do very much compared to the rest. All these microphysics actually seem to be the most dependent. So not even changing the time step of the land model seem to do very much with regard to impact of time step on forcing. And then, of course, we'll always go to shortwave cloud forcing. And okay, there's some changing with a shorter time step, but except for the first strong going from 1 to 2, it's have a strong increase in shorter cloud forcing, and then it's relatively flat. Please notice, I forgot to mention the last figure, that the Hofer parameterization, which is in green lines, and the standard actually are very similar to each other. So even though, just increasing the limiter for NIMAX didn't really do very much for these forcings. And then, of course, then you get up and find out where do you find the change in the time step, and that's long wave cloud forcing. So as seen below, this is on a log scale, so, and it's basically a straight line on the log scale. So there doesn't seem to be any convergence in just reducing the time step could increase the long wave cloud forcing. At some point you have to choose, of course, but then it becomes a bit more of a tuning than actually physical reasoning behind it. Also to show that it doesn't always only NORSM, it is then Thomas Donacci also included a updated version of PUMAS, where basically this is also long wave cloud forcing. It's the same, but it has different scale because the PUMAS version has a much higher long wave cloud forcing in this setting, but it's still the impact on long wave cloud forcing for shorter time step is the same as for all the rest of the experiments. So summary, 2 alternative formulation ice number are available, and in many ways what just surprised me, was really interesting to see perhaps an observation from David, was that the differences between resolutions are larger than between the parameterizations. So I understand what's going on there. Long wave cloud forcing does not converge with an increased number of microphysical steps, and another convergence is not dependent on choice of ice number limiter, model resolution, model versions, or even external forcings, at least within a reasonable amount of variation on external forcing. Yeah.
All right, thank you. Does anyone have any questions? Again, feel free to put them in the chat or ask directly.
I have a question.
Yeah.
There's this, the robust signature seemed to be an increase in long wave cloud forcing, reducing the MG steps, MG time step.
Yeah.
Is that consistent with what Sean Santos's paper had found? I know he did a similar time step analysis.
At least what's written is they only did it for the ice number, not for the forcings. But
I'm sorry, I didn't get that.
At least from my impression, from the paper, they only did it for ice number and not for the forcings.
I'll have to look at that paper. I know he had precipitation he was looking at a lot, and I can't remember if there was long wave cloud forcing, but I know he did a large convergence. You know, he tested a lot of these MG time steps that you're testing.
Yes, I know, but I couldn't find anything about forcings.
All right. That's all I got.
All right, thanks for the question. I think we should move on to stay on schedule. If there's other questions, we can address them in the discussion. And our next speaker is Rich Neal.
All right, I'll turn my camera on. Just share. You see that, Nick? Yeah.
Yep, looks good.
Go. All right. So this is a few slides about the continuation of understanding some sensitivities and when we've been trying to increase vertical resolution for CAM7. And just as a reminder, I think Julio may have said it. So, you know, our target from where we are now with Wacom and CAM6 was to develop a workhorse CAM7 version, which will be 93 levels for the high top and 58 kind of using that also for the low top. And this was an attempt, probably imperfect, to satisfy CAM and Wacom needs. And the critical thing, that there are 16 levels that have been added to the free troposphere and stratosphere. And we've kind of, you know, done some very objective work to understand the QBO wave forcing as it relates to that. But we've also added 10 levels into the boundary layer. Below, as you can see on the left here, around about 600 millibars or so. So this red one is a set of points is where we are now with our kind of most up-to-date 58 level version. There's a little bit more kind of nebulous about a justification for that, but essentially, you know, stratocumulus cooled stratocumulus tops and turbulence probably does better with high resolution. But this is fraught to a certain extent. We've increased vertical resolution very sparingly in the past, with sometimes with difficult consequences. And this is probably no different. And just to say, we had initially L58 problems because of the model seemed to be crashing surface fluxes right near the surface, near very hot and dry land and ocean. So this talk is kind of aimed at understanding some of the sensitivities as it relates to convection and what we've looked through over the last year. And I didn't mention, but all these people up here have been great help. So the kind of framework will be single column simulations, and they'll be over tropical West Pacific for these, several 20-day periods or so. And so here on the left, we're showing convective heating. So this is a measure of convection throughout this period for the different resolutions. L32 is CAM6 as it exists release, and then this is L58. And then, you can say a number of qualitative things about it. 32 to 48 is predominantly tropospheric increases in resolution away from the boundary layer. And there are some differences, maybe in the depth, the convection topping out a little lower at L48. But it is when you get to L58 that you start to see some more than qualitative differences. But actually, one thing that you will not see necessarily is the very near surface layer, because it's very thin at 58 levels, around 40 meters versus 120, I think, for 32 levels. But essentially, if you look at that lowest level, and here is an average in that period, and I've thrown on here as well a very high resolution version, 256 levels. But essentially what you see is, as you increase vertical resolution, particularly near surface level, and you get very strong convective cooling here. This goes all the way up to 40 Kelvin for the 256 level, but the 58 level is of order 20-ish Kelvin average cooling that comes from the convection. So question is, how does that manifest? Is that important? And so what on the left here is essentially just taking that lowest model level convective heating, cooling, obviously in the lowest level tendencies. And we're distributing through these different vertical resolutions for the whole period of Togoko. And you can see quite nicely that, as you go from the coarser resolution near surface, this L32, L48, through 58, 256, you're getting very intense time step cooling values, of -60 in some cases Kelvin in that very thin 20-meter level. And it's not converging, to 256, which is, a thickness of 15 meters. These tendencies don't seem necessarily to be converging. And so, these are huge cooling. What's happening? Well, of course, if you flip over to what's compensating that club on the right-hand side, you can see that there's, at least in the distribution, I'll demonstrate later that it's like for like, as in when there's a strong time of ZM cooling, then there's a equivalent heating in club. But essentially, there's this big push-pull in the very near surface related to this increased vertical resolution. As always throughout this, does this matter? Are there consequences of this? For precipitation, in terms of when you look at these three, this is a log scale now of precip values, again, for each of these PDF, compensated for each of these bins. And, you're hard pushed to say, there is a particular consequence for any of these resolutions. So they're clearly at a time step, on a time step basis, compensating. And so, you ask yourself what's happening. And so if we look at convective mass flux, updraft and downdraft, which show here. And so we have the three resolutions that, we're main focus, but then also this 256 level. And so for the updraft mass flux, there is no, they're very similar in the surface, and they're equal also the downdraft. But of course, this is going right down to the surface. So the L58, if you think about mass flux convergence and divergence, you're really intensifying that, because below the parcel launch level, all the mass is being extracted. And there is a limiter, and in the 256, you can see that the limiter is in action here. But also, more consequentially maybe, is the downdraft mass flux does not decrease with this smallest, lowest level. Really, really tells you that the mass flux is being dumped into this lowest level. And that is the consequence of that is these intense convective heat coolings. So how have we kind of tried to address this, modified this? So we've made somewhat of a simple fix. So on the left-hand side, this is the default CAM6 and all the way back to CAM35 ways in which the deep convection specifies where a parcel will launch. So it's the moist static energy consideration. So it's the maximum of that value. And as you'll see, it's almost always next to the surface, in the surface level, maybe one level above, over the ocean in the tropics. And of course, as this surface level gets thinner and thinner and thinner, then that kind of compresses where this level is launching parcels. So that doesn't seem realistic. So what we've done is implemented, effectively a length scale here. In terms of we're now determining that the boundary layer has to be well mixed. It's not taking anything from the club boundary layer. It's a pseudo simple boundary layer within the convection, saying the mixing within the boundary layer determines the depth, the level at which parcel is now allowed to initialize, and also the properties. So there you get this kind of more flexible length scale and a more kind of realistic sensitivity to where the boundary layer depth is doing. And in all the simulations that follow, actually this length scale we have is like half the depth of the boundary layer. So what does that do in terms of where the parcel initiates? And so this is quite a nice plot, I think, for this whole Toga period. We can see that the solid lines here are the original resolutions, and they just essentially, this parcel level just compresses to the surface. So the red is underneath the blue, and the green is just the very near surface level. Now with this modification, you launch the parcel at generally a higher level, but this varies with the ambient conditions, which you probably should do from the perspective of sensitivity of convection. In terms of precipitation, it has actually a nice effect in this somewhat constrained system of a single column model. And you can see that, for the most part, all the lines overline the dotted line black, which is the observations. But in some of these interim periods, the solid lines, all resolutions were too wet. And this kind of higher sensitivities kind of led to a better match. But this is a constrained system, single column. It's kind of easy to get precipitation right to a certain extent. This is still, I think, good. And so what has happened to the mass flux distribution that we talked about in the convection? And so you can see we've added on now from this, this modified parcel calculation, and we've now moved from this kind of ever decreasing thickness that the mass flux just originates from that level to something that is, more gentle in the way that the mass flux decreases with distance from the surface. And also the downdraft does not now just pile all the way into whatever the near surface level is now determined that below where this convection parcel initiates now, it has a much more distributed mass flux divergence. And so when you contrast this with the original plot with the big spread and the push-pull, so now the next one I'll show is what happens if you now apply this ZM2 modification to all the resolutions, and they all collapse to something that is similar amongst the different resolutions, but also much lower values. The question is it too low? I mean, this is where it comes down to, is it up front, was it erroneous? And the question is, what is this length scale, and how do we determine what that length scale should be? And again, you ask the question, does it matter? So for precipitation, it doesn't really matter still. There are a few stronger events, and that's generally the case, I think, when you do this modification, but not a lot. So the final few slides, we'll look at AMIP simulations. So we have AMIP simulations we've done to try and understand these increased sensitivity, increases in vertical resolution. This is the plot where I said before, we can determine that the intense convective events that lead to these strong near surface coolings are coupled to a co-located in time near surface warming from club. And so this is just essentially a scatter plot showing club temperature tendencies at the surface versus convective. And clearly, particularly when the convection tendencies get high, and these are high, 30 Kelvin per day, and daily values these are from a year of the AMIP simulation. We can see that obviously the 58 level with this thin surface level boundary layer levels really doesn't matter, particularly out to these strong convective as determined by the cooling that occurs right near the surface. And then, like I say, with that, at the same time, there is strong warming from club. So now going to these PDFs, same as before, but much better sample with looking throughout the whole tropics for a year of data here. So it's a year of daily data. And so it's kind of nice that when we look at the PDF of temperature tendencies near the surface, we can see that the 32 and 40 levels are almost indistinguishable, which says, the boundary layer really is the key here for determining, no surprise, these boundary layer tendencies. And then the 58 level here has this long tail, and the mean values are much stronger. And again, it's compensated for in time, as we showed in the previous plot, by club. The red here is what happens if you take the 58 level and then apply this parcel modification. So you're going from green to red here. So it's a pretty big change. Question is, what should our target really be for this? Should it be the 32, 48 level kind of characteristics, or is this better? Should we have a deeper length scale associated with boundary layer convection that makes it somewhat independent of the vertical resolution there? And just a couple more, just to illustrate, 50. I think the point had to be made that when we first added 58 levels, it degrades the simulation quite a lot in terms of precipitation. It's subtle, but I think looking at these scores, for example, in DGF, it's 1.1 through to 1.4. That's a big change in total precipitation root mean squared error. And also, summertime, which is always the hardest one, that's a big degradation. So, the integrated effect is a degradation. And, these characteristics also play out in terms of this is a low level temperature cooling, mean cooling in the lowest model level from deep convection. And you can see it's, throughout the whole tropics, it's cooling all the time, not all the time, but on average by minus 12 Kelvin compared to in the thicker lowest levels of the less resolved near surface around about 4 Kelvin. And then, nicely to a certain extent, the ZM2 added to this really moderates that to be less in some cases than the deep, than the default boundary layer cooling. Contrast that also with the club. So this is the push-pull. So it's warming everywhere in that lowest model level. Not, in the exotropics, it's very similar to these at 3248, but in the deep tropics, it's doing this push-pull with convection. And then with the ZM2, you moderate that. And then these tendencies are lower still. So like I say, just to reiterate, we may want to moderate that through a thinner length scale that is assumed by this parser modification. And that's it. And so just to, I'll let you read the first 2 sets here, just a reiteration of what I talked about. But I think there's a few things just to maybe talk about is continental convection. So we've looked at it, continental sites, Southern Great Plains site. It's this modification has a big impact. It's not desperately clear whether it's better or worse, but it does have a big impact that I need to look into more. With respect to some of the ZM or the other parameterizations, I'm sure there are level dependencies that still exist that need to be uncovered. But it does feed into this question from the development perspective of AMWG. How much life does ZM have? How much work do we need to put in to make this play well with the rest of the physics? And that's it. Thanks.
Thanks, Rich. Adam, do you want to ask your question in the chat?
Oh, sure. Yeah, I was just wondering, I'm wondering if it's not really club, but the surface fluxes are, like I said, getting ginned up by this sort of large change in T-bot, since the surface fluxes are the difference from T-bot and TS. And it just shows up in club because that's where we apply them.
But I mean, it does not show up in, I was looking at extremes to pick out, at the end of the PDF. And you look at latent heat flux, there's no difference in the extremes in the 4 different panels here. I was going to put it in, but yeah, there's no impact. There's something in compensation that's going in internally in time, in the time loop, that kind of negates a lot of, not all of it, because obviously it's having an impact when you look at the scores here, but there's something something that's being negated, being compensated for before the surface is coupled. I guess you know more than me. So.
All right, so it's still to be determined exactly what it is.
Right. Yeah, that's why I keep asking. Does it matter? It looks bad, but does it matter?
I guess that's the bigger, more important question. Yeah.
Yeah.
All right. Thanks, Rich. I think in the interest of time, we'll move on. Thanks, Adam, for the question. So we'll move on to our final speaker of the session, who's Michael Brunk, who's going to talk about the Activate.
So can you see that?
Yes.
Yeah, okay. So
sorry, do you want to be in full screen mode?
Oh yes, I do want to be in full screen mode. Yes, I do. Okay. So I'm going to talk to you about Activate. This is a field campaign off of the East Coast of the US. And this study includes a lot of, you see a lot of names there. They're from the University of Arizona, NASA Langley, where the flights are flown out of, PNNL, Germany, and the University, Vince Larson from the University of Wisconsin, Milwaukee. So the motivation for this is the fact that clouds have long been poorly simulated in models. This despite there being a lot of field campaigns and numerous studies trying to work on rectifying those that poor simulation. So we asked in the study, how can we use the Activate observations to provide some insights into the evaluation and improvement of model simulation of clouds? But we focus on the turbulence aspects of those processes. The reason being that turbulence is a key component to the creation and maintenance of clouds. For instance, the turbulence below cloud is the main determinant of the updraft velocity, which ends up determining how many of the aerosol particles actually get activated. So, of course, turbulence in the climate models has to be parameterized, being a grid cell, subgrid cell process. And in CAM6, of course, we all know that this is done by club. And club, being a higher order of parameterization, needs to assume a binormal PDF shape for its closure. And that binormal PDF was verified in the development of club from observations of subtropical and tropical cumulus and stratocumulus, which you can see on the right here. So this needs to be further validated globally. And we ask for this study, is the binormal PDF assumption used by club valid for the mid-latitude clouds observed for Activate? So what is Activate? Activate is a NASA Earth Venture Suborbital 3 investigation involving air flights coming out of Langley, Virginia. And there are 2 deployments done per year. One is in the winter, looking at cold air outbreaks, and another one in the summer. And this is done for all the way back from 2020 to this year. And the unique thing about Activate is that there are 2 aircraft that are flown in coordination. A high-flying aircraft, which has a LiDAR and a scanning polarimeter and launches dropsondes. And in the boundary layer, we have this low-flying aircraft, the HU-25, that does the stair-stepping maneuvers. the stairs, the steps are called, we call them level legs, and the a full set of the level legs is called an ensemble. So for the cloudy ensembles with this cloud, you have the below cloud base and above cloud base legs, and then you go up to above cloud top and below cloud top, and in the middle, the airplane tries to get as close to the surface, the ocean surface as possible, which is at about 150 meters, sorry. And so this is the minimum altitude or min alt leg. For clear ensembles, we just have above and below cloud, a boundary layer topside, and then it goes down to near surface, and you have a remote sensing leg and a min alt leg again. But it's we don't use the remote sensing leg since we have the min alt leg in this study. Please note these acronyms because you're going to see them a lot later on. The turbulence we derive from the meteorological instrument on board the HU-25. It's called TAMS. And what we do is use the classical definition of some quantity X can be decomposed into a mean over a period of time in the turbulent perturbations. So that's how we do this. The time period is each of the level legs. So we do this for each of the level legs, and then we can get other quantities like the second order moments, which basically are the variances. And the turbulent kinetic energy, of course, is 1/2 times the sum of the wind variances. We also get other quantities as well, but for the interest of time, I'm not going to go into, we're not going to discuss those. We're just going to discuss the variances and the TKE. And of course, since we want to get some implications for model evaluation and improvement, we need model simulation. So what we do is we performed 15 days of an enhanced instantaneous output at 30-minute time steps over a number of years. And we do that for 2 periods, February going into March and August going into September, which corresponds to roughly to when the 2 deployments were done in 2020, which is the data that I'm going to be looking at for here. And this is for atmosphere land only simulation, AMWG simulations with prescribed SSTs. Then how do we characterize the turbulence in the boundary layer from the observations? And I do this by looking at the frequency distributions, which is what's shown on the left for the cloudy ensembles, for the level legs within the cloud and then below the cloud. And I'm showing both the winter and the summer deployments. And you can see there's a distinct difference between the winter deployment frequency distributions and the summer ones. And that's probably better described, summarized by these panels in the upper right, which shows the median and mean and interquartile ranges of the observations at each of the level legs for the cloudy ensembles. 2 things to point out. TKE is lower in the summer, clearly. And also our highest TKE is actually at below cloud top in both seasons, both the winter and the summer. So, in the observations, the maximum TKE is within cloud. You can also see that just by grouping all the cloudy ensemble observations. You can see that in the percentages in that table. But if we go to the model, CAM6 simulations, the 15-day simulations, and look where the maximum TKE for all the cloudy columns within the activate domain, or only over the ocean, overwhelmingly, the model wants to put the maximum TKE below cloud, not within cloud. So there's a distinction between the model and the observations there. Of course, we want to answer that question, is the binomial PDF valid in CLUB for the for these mid-latitude clouds. And how we do that is by looking at the observations, doing a bivariate frequency distribution here, given for the liquid potential temperature perturbations as a function of the vertical wind perturbations. And that's what this column is here. And you can clearly see by the circular or the elliptical shape to those bivariate frequency distributions that binormal PDF is indeed valid even for these mid-latitude clouds. You also see that by looking at the symmetry of these univariate frequency distributions. But if you compare the min-out to the below cloud top, you clearly see that it's being skewed in the vertical velocity direction at the surface or near the surface in that min-out. So what's going on is that the vertical velocity distribution is getting wider as you get close, going from the top above the boundary layer, going closer to the surface, whereas the liquid potential temperature frequency distributions are not changing very much with height. The last thing that we could do is we can directly compare the frequency distributions from the model simulations. That's what's on top here for cloudy conditions for all the below cloud grid boxes, except for the lowest model level, which is separated. And this corresponds to roughly the below cloud base level leg and to the min-out in activate, which is on the bottom. And I'm looking at, in this case, the wind variances. And if you note that the difference in the ranges in the model, the x-axis is for the model and the observations, you see that the simulated turbulence is weaker than observed. This was also noted for comparisons with the Socrates observation, specifically for CAM 6. But the other thing that you can note is that there's a difference in the width, the relative width of the frequency distributions. So in the model, the vertical velocity variances distribution is widest, whereas in the observation, it's widest in the zonal wind variance distributions. So there's a clear distinction between that and that case. The reason why we include EV2, the version 2 of the E3SM model, in here is because in the development of version 2, the E3SM team did a retuning of the club parameters, and we wanted to see if that had any effect on these mid-latitude clouds, and indeed it does, because you could see that the vertical velocity variance distributions are actually narrowing, so it looks closer to observations, even though the turbulence is still weaker. But there's still room for some improvement, obviously. One being the obvious one is that the horizontal wind variances still look very much the same as before. So some additional retuning is necessary. So here are the conclusions, the takeaway points. I'm just going to throw these up and add one more point, that the full set of these full 3 years of these observations would be very helpful to anybody who is doing any further retuning of club to provide physical insights and also for validation, for data for validation. I know there was a few talks yesterday that was dealing with club retuning. So with that, I will open the floor to questions.
All right, thanks. Is there any questions? Oh, Julio's just got a question in the chat. Do you want to just ask it, or would you like me to ask it?
Yeah, sure. Hi, Michael. I was just wondering, is it really possible to distinguish between U prime and V prime from a few, from a few flights? It seems like if you had many flights in lots of different directions.
Well, yeah, I didn't put that on here.
Okay.
I forgot the number of flights, but It's not a few flights, but the full set of 3 years would be much better. Trying to go back to that. So I forgot. I should have. I forgot how many flights that there were from both the winter and the summer campaigns. But it's not just like a handful. It's not a handful. It's like tens of flights at the very least.
Okay.
Any other questions? The bulk. Oh, I was gonna add.
No, go ahead.
Go ahead. I was gonna say the bulk of the flights. I can't. It won't let me go back. Let me escape. No, it won't let me do that either. A bulk of the flights are what we call we do a couple. We did a couple in the winter and a couple in the summer of the first year, 2020, where we did process studies where we focus on a particular day, during a particular day, a process, and we did a circle in the winter where the circle, and that was for the LES modelers in this group. But the bulk of the flights are actually what we call these statistical surveys. So it keeps doing that. It goes out. We go out from Langley, out a ways, and we go sample the clouds, and we do those ensembles repeatedly, over and over. So we get a lot of sampling of various cloud conditions, and more clouds, more cloud fraction versus less cloud fraction. So we get some good sampling, and like I said, it will be better when we have the full set. But we wanted to get something out using the preliminary first year of data.
We've got another question in the chat. Tomas, do you want to ask it?
Yeah, thanks. I'm not actually 100% sure here, but I believe that in club, DKE is in fact just the W prime component. Is that right?
I am not sure.
I think Thomas is right.
Yeah. Oh, yeah.
So perhaps then the comparison should be in your measure to DKE should be just W prime squared if you wanted to.
Okay.
Right.
I would say that it's a little. I think it's a little unclear because there is a W prime squared, a U prime squared, and a V prime squared.
Right.
But never are they summed together and fed back into any of the equations in club. Yeah. That quantity, as far as I'm concerned, that triple sum is just a diagnostic output that you can look at.
Yeah, are there even prognostic equations for U prime and V prime separately? Squared, I mean, yeah.
It spits out. Oh, go ahead. I'm sorry.
Go ahead. Oh, there are equations that are, but it's not the quantities that are really that the PDF is being used for. The like W prime theta L prime and W prime Q T prime. So those double ones, there are equations for U prime squared. That's why Vince had suggested that the problem that you see with this, with the U prime squared and V prime squared frequency distributions might be the fact that one of the parameters that are used for the TK, I lost my words, but the one term in that equation eddy diffusion term needs to be adjusted. But in the paper, I don't actually could directly compare the model TKE. But the model TKE to the observations. But that's a good thing to note, that it's only a function of W prime squared.
Yeah, I was looking at the code, and I mean, Club does spit out a U squared and a V squared.
Right.
But I think it's a diagnostic. I mean, it's not one of the prognostic variances.
Yeah, it's more of a diagnostic quantity, I think. But there is an equation to determine them. So, see.
And yeah, I think we have that off in CAM 6, and because that's prognostic momentum, and so in the default model we have that off. So right now it's just diagnosing U prime squared somehow. Does that sound right, Julio?
I think so. Am I muted? No. Yeah. No. That sounds right. Yeah. Oh, Meg is saying, oh.
That's what I was saying. They're prognostic equations,
right.
But I don't think those. Yeah, I'm not sure that those are actually used, but at least not in the model. Maybe they're intended to be used at some point.
Yeah, I mean, we're thinking about turning on prognostic momentum for CAM 7. I think Collins touched on it, but right now it's not the default setting.
Okay.
All right, well, thanks. That's been kind of a good continuing discussion. We've got a few minutes left till we're officially meant to adjourn. It may be worth coming back to some of the earlier talks. I think I have in my notes David's sort of request for some help with CAM debugging, or at least someone who knows what they can do with CAM. So I'm not sure if we want to revisit that discussion. Oh, I see it. Sorry, Leo Donner has their hand up. Sorry, I did not see that earlier.
Yeah, if it's okay, Nick, I had a question going back to Rich's talk, and that involved, the precipitation PDFs seem to be collapsing quite a bit despite the changes that were made in the number of levels. But Rich, I was wondering what was going on with the stratiform clouds and water vapor distributions. Was anything happening there that was significant? And I'm even wondering from the point of view of the water vapor, if perhaps some changes are occurring in the radiation balance in the long wave cooling that might be feeding back in the global to the precipitation and some of the numbers you showed that weren't so good on the RMS.
Yeah, I'm not sure I have a good answer for that. I mean, goes back to Adam's question, really. It's just this compensation within, a time step within a day between the two, push-pull of club and ZM in the lowest model level. There doesn't seem to be a consequence for that on surface fluxes. I'll be honest, it's not clear to me what the exact consequence of that big push-pull is at the surface there. And for, mostly, obviously, the push-pull is beneath convection, but in the stratiform regions, off the coasts of Africa and South America, there are differences in the 58 level, but it's not due to the convection, I think.
Okay.
One of the many figures I looked at was looking at the extremes and the surface extremes and surface tendencies, near surface tendencies in club. And actually, there is some very odd behavior in the kind of stratocumulus regions where there are if you have a very thin surface layer, it does not seem to have a very strong heating extreme, whereas the 32 level does. So I think they're underneath the stratocumulus near the surface, there's definitely something that needs to be looked at to see exactly how it's behaving in the new resolution.
Yeah, I'm wondering too, maybe about detrainment changes from the ZM that might be feeding in even at higher levels. So, possibly.
Oh yeah, that's a different. Yeah, I mean that goes back to talking about our. Did we talk about it this week? The moisture transport into the stratosphere, and there's definitely some sensitivity to when you include this modification. It looks. I think originally when we put it in, it made things slightly worse. We have made modifications to improve that, but I think in general it did make this stratospheric and upper tropospheric humidification drying rather worse. So there's definitely the top to bottom communication in that. Yeah.
Okay. Yeah. So some interesting issues there. Thanks, Rich.
Yeah. Thanks, Lou.
I kind of have a question that Rich, you sort of raised in your conclusions about, how much more life does ZM have in it? And I just wonder if part of that sentiment is sort of driven by ZM fatigue, and versus the fact that it's lasted so long is a testament to its robustness. I don't know. What are the downsides of the ZM scheme from your opinion or anybody's opinion? What don't they like about it?
My impression is that it is the assumption basically of an exponential mass flux profile in the cloud plume ensemble that is needed in order to close semi-analytically the solution for the ZM cloud calculations. I think is a very strong assumption, and it tends to result in heating profiles that tend to be towards slightly bottom heavy biased compared to reality. That's my impression. I'm just putting it out there. I don't know whether that's what other people also think or not. But I have the impression that it is that the shape of the heating that you get out of ZM tends to be rather rigid, and it may not reflect the variety of convection regimes that we have in reality.
And I can speak to that theoretically, but I don't know if that may or may not be related to the fact that ZM, when ZM is allowed to sort of do as much work at high resolution, it has a tendency to interfere with mesoscale organization, and that's related to the bottom heavy heating profiles, but it's not clear how to me it's not clear how to make ZM behave at higher resolution when the equilibrium assumptions that go into the closure aren't really satisfied. Of course, I can't think of any convective scheme that where we will be able to do that. But I think the resolution insensitivity is a problem.
Yeah, so Julio, just to the thought I would have, I agree with your comment about the closures breaking down as the resolution gets fine. The thing that's always struck me is this issue of a single plume, really, as opposed to multiple plume. And you know, yesterday, for example, Ya was making the case for shallow convection, even multiple plume, when, well, if multiple plume is necessary for shallow, it's certainly for deep. And I think that's part of the problem with the heating maximum being too low. If you had multiple plumes, you might be able to overcome some of that. And it might be easier to explicitly build on a mesoscale component to get some of the upper level heating based on a lot of detrainment coming from the shallower members of the multiple plume. But when you do it with just one, things are a challenge. And of course, going all the way back to Arakawa-Schubert, the argument was multiple plumes. You know, having said that, you know, GFDL also in CM4, we're down again to a single plume for deep convection. They are somewhat easier to tune. I think there's maybe a practical affection for them in some ways because of that. But to me, it's the idea of reducing an ensemble to a single plume that may be the biggest issue. And I do think that eventually, if we want to do things like aerosol convective interactions and putting in the kind of microphysics in convection that we need to do some of the possible anvil feedbacks and things like that, we're going to have to be really concerned about vertical velocities. And then it's going to be really hard with a single plume because there's a lot of nonlinearity involved. So to me, it's a generic comment about any single plume representations. ZM does a pretty good job if you've only got one plume, but beyond that, I think there are concerns.
Well, Leo, isn't it true that even that it is kind of difficult to come up with a sensible vertical velocity equation or approximation for ZM?
Yes, I think you can do it, but the problem is the buoyancy that you've got in ZM. I think it really struggles to come up with vertical velocities from what little measurement we have of it that are realistic. And I think that there's just too much nonlinearity in taking a set of multiple plumes, which might have a reasonable vertical velocity equation. So like the ones in Joao's EDMF scheme, for example, that Adam's become very familiar with, that it's very difficult to collapse that into a single plume. And even in the multiple plumes, the entrainment is such a big control on the vertical velocity that there are issues there, but it's really tough with a single plume. So that's what my thinking has always been. It's so tough. People have just wanted to say, collapse it down and then have some very strong tuning parameters like the entrainment or, things like that, things that maybe drive a cold pool or something in a simple way to try to overcome it. But the space to play in, I suspect, is limited. We've become experts in playing in it, though. And I'd say this of the single plume for deep convection at GFDL also, it's not exactly like CM, but there's kind of a similar underlying philosophy, I'd say.
These are all great points. And yeah, I mean, the Club MF stuff, when we've been looking at it for deep convection, you do get plumes terminating at various heights throughout the ensemble column. And so you definitely see the impact of that ensemble. Whereas, you call ZM a single plume and it's a bulk plume, but it actually...
But with a very restrictive assumption about how the mass flux is going to the... Yeah, and that's an important point, Adam, but...
Well, I just want to make the point. If you read, the original papers, it says that the ensemble is supposed to be a bunch of plumes that detrain between 500 hectopascals and the top of the plume, which is the undilute plume member. Yeah. And when you look in the code, there's a limiter on the entrainment rate for the plume members, such that they actually all terminate at the same level, we found out. And so it does actually, this bulk plume does act like a single plume because it detrains at one level, whether you're running at L32 or L128 or something. So it does act like a single plume, and just wanted to make that point.
Yeah. No, I think the assumption there that you can sort of start out thinking of individual plumes, but then the mass flux is the same through the base of all of them, which is a pretty big departure from Arakawa-Schubert thinking, or even the Donner multiple plume. Any of those don't really make that. But you're right, when it comes down to it pragmatically, it's kind of acting like a single plume, which is, it's the beauty of the simplification of it in a certain sense, but it's a big drawback when it comes down to some of the contrasts you would see if you really had more independent multiple plumes detraining at different levels. With a lot of them, what happens with the Donner parameterization, a lot of them detrain in the middle part of the atmosphere, and that's the building block then for mesoscale anvils and downdrafts and all kinds of stuff. It's hard to get that with a single plume.
Yeah, it's the constant cloud-based mass flux for all the plume members makes it sort of analytically tractable, and as Thomas says, it makes this sort of very smooth exponential that doesn't look very realistic. It looks like a cartoon.
Yeah, exactly. Yeah, exactly. That analytic beauty is really nice, but you pay a price.
Mm-hmm. And when we try to use consistent microphysics, MG microphysics in the CM scheme, we get a really weird solution.
Yeah.
And so the ability to unify our microphysics from the Stratiform and ZM is being doesn't look like it's realistic to do in practice. So
yeah. So Adam, I'd really like to underscore that one about 5 times. That has always been my main argument for going to multiple plume on deep convection. I think once you start to have things that depend, for example, on updraft speed, like some of the microphysics, you're going to really have problems. Even if you could somehow define a proper updraft speed, as Julio was saying, for a single plume, when the reality is they're multiple, I think it's going to be very difficult. And this is one reason people have, for 20 years, I would say, talked about how important it is to put microphysics in deep convection. That's something like PUMAS, or that we are using in the stratiform clouds. But it's been, every attempt has sort of had some real difficulties. And I think this is part of the problem. It's, a single plume just won't do it because the microphysics is really nonlinear in the plume properties.
great points. All right, I'll stop the Adam Leo show.
Yeah, thanks everyone for listening to us.
No problem. Nick Davis had to leave, so I'll take over chairing. Are there any other question or comment that are seen as urgent, as we're a bit over time already?
I'd like to ask the question, who else is worried about the fact that the top of the atmosphere radiation balance or imbalance in simulations is so sensitive to microphysics substepping and what should we do about it? Because the original idea by Ju last year, when he made his presentation about the LGM tuning for CAM, was that eventually, if you use a sufficient number of substeps, you get the convergence, you get the solution that is unique and does no longer depend on substepping. But in fact, on testing that assumption, we found that it isn't quite the case, that the more steps you make, the greater long wave cloud forcing you get, and that directly reflects on the top of the atmosphere radiation balance of the model. Should we consider the number of substeps in the microphysics a tuning parameter? It's a little bit of strange tuning parameter because it indicates that there is something wrong with the numerics. Or is this just my interpretation? And what do other people think about this? This is my urgent question. Sorry, I know we are out of time, so maybe we can take this.
Well, I think it is a troubling aspect of the microphysics. I don't know. Maybe it's kind of glibly optimistic to say maybe the implicit fall speed that Andrew has implemented will make things a little less sensitive. But
we tested that actually in Julio in our simulations where we grafted Puma onto our model, basically the new Pumas, And we use this implicit force speed, so it makes no difference actually. The behavior is, if anything, is even worse. So the drift is still there.
I don't understand why. How do we reconcile these different conclusions from Jiang and from you about the sensitivity? Because yeah, I seem to recall he
when we do look at the ice cloud ice concentrations as Jiang does, then it does tend towards a certain result, more or less. But the radiation doesn't, because the cloud themselves actually change.
So I guess just as a framework for attacking this, I would say maybe we should have a spin-off to look at this issue in single column. I would assume these sensitivities show up just fine in single column simulations.
Yes, I would assume so as well. I haven't actually tasted that, but it seems very likely, yes.
So in single column, we can push things to, you know, well, not ridiculous in the sense of being good, but well, we can push things to unrealistically small time steps that might show us if things ever converge more efficiently than looking at this in 3D simulations. So that's
we show only up to 16 number of time steps, but we did go to 64. It keeps going. So yes, it would be useful to have a cheaper test bed and something that can give us maybe a better handle, and lends itself also better for analysis. I think it would be great, actually.
Just watch out, since there are this strange parabola. So from 1 to 2 it drops, and then it sort of stabilizes, and then it gradually picks up and passes by the substepping 1 again. So you can't you need to check. You cannot not only check until 4 or 8. You really need to go to at least 16 to really see if it stabilizes or not.
Well, I'll just say generally, I'm not surprised that it doesn't converge. That's an uncomfortable fact I've always learned to accept about GCMs, is our model doesn't converge with decreasing physics time stuff anyways. So it's a concern.
There's got to be, I mean, I would find that really disturbing if we found that even in single column mode, when we go to 3-second time steps, you know, going to 6-second time steps makes a big difference. So I think, well, I definitely think it's disturbing, and I think we should try to characterize this a little better. And I'm talking about us. I don't know what.
No, I think this is a general problem, Julio, and it's not, you know, we've seen this also, and this isn't, unfortunately, this is not the only numerics where this kind of behavior occurs, and it is, Thomas is right, it's deeply disturbing, and we should at least maybe try to understand it better. It's one of those things people kind of know, but have not really, I would say, come to grips with. It's definitely a concern. I mean, and then it's dealt with by tuning, of course.
Right.
But that's, you know, not a good thing, really.
I suspect that there may be a numerical issue at the base where we are basically looking for the intersection of two curves by iteration, but that iteration maybe is dealing with convex problem that cannot converge no matter how often you do it. So yeah, I think there might be perhaps a problem in how that ice calculation, that microphysics calculation is done, what the sequence of operations is, and whether that's actually something that can lead to convergence. But that's pure speculation. I really don't know, and it would be great actually if we made some systematic effort to understand it better.
Well,
In
yeah,
a way,
I'll-
the good news from our simulations is that if you compare the curve we get for long wave cloud forcing from using MACMIC, is it? Yes, MACMIC equal to 6 instead of 3, the same club time step, 300 seconds. And those done with MACMIC equal to 3, it looks like the answer just depends actually on the MG time step and not on the iteration. So
it looked like the MACMIC 6 curve was always systematically higher for the shortwave cloud forcing, if I'm remembering the red line plot that you showed correctly. It looked like it systematically had weaker shortwave
that
cloud
is correct.
forcing
Yes,
than
that
any
is
of the other
right.
ones.
So yes, so low clouds are really affected by MACMIC, but the high clouds aren't so much, at least.
Yeah, okay.
Yeah, and what to say, even surprising to me was despite the large differences in ice parameter, ice limiter parameter, still the long wave cloud forcing was just shifted. So basically, the model resolution didn't matter. There was nothing seemed to matter except for this time step.
Well, I'll put it on the to-do list. I won't forget.
Why don't we conclude session here? This is good discussion. And we will reconvene tomorrow morning at 9 a.m. Mountain Time.
Thanks, Nick.
Thanks.
Thank you.
Thanks.